Finishing up these notes, we were just creeping in on 0 from the right because when we're having a limit and we're approaching 0, it means we approach from both directions. And we could make a big full table, but let's just kind of creep in a little bit from both directions and see if we see something happening. When I creep in on 0 from the left-hand side, I could use a negative. And again, I don't have to use 0.0001. I'm just getting really close to 0. I'll get farther away in a second. You'll notice for this one, absolute value of a negative is a positive, but this is going to remain a negative down here. So I actually get a -1. These two numbers actually are not approaching the same number. They're not like converging in at 0 or 2 like the other ones have been. Let's move farther away from 0 and see what happens. Suppose I went farther to the right at, say, 5. I would have the absolute value of 5 over 5, which is again 1. Well, what if I chose from the left -5? I'd have the absolute value of -5, which is 5, over at -5. I still get -1. It seems that as I'm approaching 0 from both sides, when I approach 0 from the right-hand side on the x-axis, I'm getting 1. And I am. The absolute value of 8 over 8 is 1. 10 over 10, it's 1. They're all 1, 1, 1, 1, 1, 1, 1. Problem at 0 because we can't have 0 over 0. When I crept in from the left, it appeared like I was getting -1, and I am. If I put in a -10 here, I'd have 10 over -10, which is -1, -1, -1, -1, right up to it. But at that spot, there's a problem. So again, we've got that hole there. And if you were to go graph that function, that's exactly what you'd see. Now taking the denominator off of that and just approaching the absolute value of x, again from both sides of 0, if we do it numerically, we creep. What's the absolute value of 5? 5. 4 is 4. 3, 3. 2 is 2. 1 is 1. And as I get closer and closer to 0 from the right, like at 0.00001, I get 0.00001. And if I added another 0, then there'd be another 0 here. Looks like I'm approaching 0 from the right-hand side. And graphically, that's exactly what happens with your absolute value function. From the left-hand side, I also am approaching 0 because I get that exact same function back. And so graphically, you can see that right here, I had a problem. I did not approach the same from the left and from the right, but right here I do. So on this one right here, we'd say the limit does not exist, whereas this one right here, we'd say the limit, as I'm approaching 0 from both directions on the absolute value function, is 0. All right, so that's our one situation where limits fail to exist. When the limit from the right does not equal the limit from the left. The second situation that a limit fails to exist is when f of x is, we can call this like increasing or decreasing without bound. Let's write it that way. Increasing, let's just write this. When f of x increases or decreases without bound. What does that mean? Basically, it's going to the infinities. Then we don't have a limit. Let's show graphically what that means. Okay, let's go right over here. I'm going to have you think of what the function 1 over x looks like. And we know, hopefully, because we did the parent functions on the last test, that 1 over x has an asymptote at 0, because the denominator is 0 there and does not cancel. And it goes like this and goes like this. At 0, we say the limit does not exist, because I'm heading down forever, up forever, and we will certainly not meet at the same restaurant. So we would say the limit as x approaches 0 of the function 1 over x does not exist because it's going to the infinities there. It has unbound behavior. However, the limit as I approach 1 is 1. So be careful what you're approaching. Here's another example. If I were to say h of x is 1 over x squared, we know that parent function, we had it on the last test. That one looks like this. And again, as I approach 0, it's unbound. Again, these two guys are going to be able to wave at each other as it goes to infinity, but they cannot meet because they've got that fence between them. So we'd say the limit as x approaches 0 of h of x does not exist, because it has unbound behavior. We say it increases or decreases without bound. So let's take a look at this one. It says on your graphing calculator to do this, but I would challenge you that you shouldn't need one. Think of the parent function for this one. It's actually 1 over x, which we know kind of looks like this. The 5 on the top stretches it out, and the minus 3 puts the asymptote over at 3. So if you were to go do that on your graphing calculator, you're actually much quicker just getting a sketch like this. The asymptote just got moved over. So again, down here when I say what's the limit as x approaches 3 from both directions, from the left, I'm going way down into the ground, and from the right, I'm going to the moon. There is no limit, so we say it does not exist. So second situation where a limit does not exist is when it increases or decreases without bound. The third one is the one you'll never forget, but unfortunately it's the one that almost never gets used because there's very few functions that do this. But when the function oscillates between two constant values, like f of x, I challenge you to go graph that on your graphing calculator so you can see what it looks like, but I don't have mine open right now. But when you start to get in real close to 0 on functions and it starts to do this, like you can't even see whether it's up or down, and you can't get at the limit no matter how much you zoom in, we would say that the limit does not exist due to oscillation. So again, we have 3 situations where a limit doesn't exist. Number 1, when you creep in from the left and you creep in from the right and you get that gap because you didn't arrive at the same place. So you can just wave at each other. Number 2, when you increase or decrease without bound, you shall never meet. And number 3, when you oscillate and zigzag back and forth so that we can't even tell what's going on there. Those are our 3 situations, and that's starred because it's going to be asked on your test. So this says sketch the graph and then determine the values for C for which the limit exists. And it just says to sketch the graph, so you just need to have a good idea what it looks like. It doesn't have to be perfect, but again, it's piecewise. And it's triggy-wiggy. Trig functions, we usually have our scale go from 1 and -1 because that's their range. Unless there's numbers in front, then sometimes we'll go up to 2, down to -2, but you don't need to have a whole lot of expansion on your y-axis. Our x-axis are angles, and we usually run those at the pi halves intervals. And when you graph and use zoom trig on your calculator, I'm just going to do a few here like this. All right, so let's go graph these in their pieces. To the left of 0, I'm graphing the sine function. I need to know what happens on the fence. The sine of 0 is its y value there, which is 0. So 0, 0 gets an open dot because there's not any equal. And then what I do to the left is I do my sine wave. And sine negative pi halves is -1 and a pi at 0 again. So I'm doing this over here. And I just sketched that. Next, I need to know what happens between 0 and pi. So I have a fence at pi. I'm going to see what happens at 0. 1 minus cosine 0. It's 1 minus 1, which is 0. Okay, so at 0, 0, that's going to fill in that empty hole. At 0, this function is 0. 1 minus cosine pi would be 1 minus -1 or 2. So up at pi, I'm going to be up at 2. And then I do kind of the cosine wave between. It doesn't really matter what you're doing between them if you're just sketching it, because we're just simply looking for where the limit exists. And so you just need to know that it's going to continually go there. So It actually goes, I think, a little bit like this curved. And beyond that, I'm going to do the cosine wave when x is greater than pi, but I need to see what happens at pi. Again, we go to the fence. Cosine pi is -1. So I'm going to have an open dot there, and then I do the cosine wave. Like perhaps I go out here to 3/2 and it'd be at 0, and it doesn't really matter except that so I can see that gap there. Again, it's a sketch of a graph. It doesn't have to be fantastic. It just needs to be good enough so I can determine the values for which the limit exists. All right, it's easier to figure out where doesn't it exist. Is there any place where the limit from the left does not equal the limit from the right? The answer to that is yes. At pi, we are at completely different places on those two roads. Is there any unbound behavior? And is x, and there's not, because this is going to continue to oscillate over here, and this is. So I really only have one problem area on here, so I will exclude that from my values. So there is a limit everywhere from -infinity to pi. At pi, I've got a problem, but when I union it with pi to infinity, I'm good. So some people would say everywhere but at pi. True. But this is the notation for everywhere except at pi. All right, I'm going to go a little bit farther. This is where the notes were supposed to end today, but let's go kind of summarize this. Actually, yeah, let's go do it. So a limit does not exist at C if. Let's see if you've got the 3 memorized. If, when we come in from the right, and then we drive in from the left, and we don't end up at the same place. If the function increases, can I go like that, or decreases without bound at C. Technically at x equals c, but if we're heading to the infinities, we will not have a limit there. And last, if f of x oscillates, which will never use, this is your big gun right here actually, oscillates at c. And oscillation doesn't mean it's going up and down. It means it's getting closer and closer and closer so that you can't even see. So we wouldn't say the sine wave oscillates at C anywhere because I can see it. There's my limit. I can see it. What's my limit here? I don't know. So let's go take a look down below, and we're going to analyze this sketch. So it says, find the limit as I approach 3 from both directions. So let's come in from the right and approach 3. It really doesn't matter what's happening here, here, or here. Okay, I'm approaching 3. Here's the road that leads to 3 from the left. From the right, it's this one, and I ended up there at 3. There was a limit. F of 0 is just the y value at 0. Right here, solid dot at -2. Limit as x approaches -1 from both directions. Well, from the left, I travel in, hop over the hole, go to the moon. From the right, I travel in and dig into the ground. This would be a D&E. And if I had to say which criteria, I would say because f increases and actually decreases without bound. All right, so next it says what's bigger, f of 1. Well, what is f of 1? F of 1 is the y there, it looks like about -1. What's the limit as I approach -2? And again, the limit is where am I? I'm approaching from both directions. So I'm approaching -2 from the left, boom, from the right, boom. So the limit as I approach -2 is the y value there, which is 2. F of -2 is 0, so be careful with that. So it says which is greater? That one. For what values of c, that means when x is c, like 4 or 5 or 6, does the limit not exist? There's no oscillation on here, so we're not looking for that. We do have unbound behavior at x equals -1, so we'd say at c equals -1, we've got an asymptote right here, so that's a problem. No limit exists. Is there any place where the limit from the left doesn't equal the limit from the right? AKA, there's a big old gap in the graph. The answer would be yes, at 0, because when I come in from the left and the right, I do not meet up. And at 2, same thing. So basically, you're looking for gaps and asymptotes. What are you looking for? Gaps and asymptotes. That's really where our limits don't exist. I said I'd keep it to 15 minutes, so that's where we will quit, and we will pick this one up. We'll do this for like the first 10 minutes tomorrow. I think we'll have a little notes, and then we'll do a learning goal problem. That's it. So we'll have about 10 minutes tomorrow, and then you can work the other 40. Have a good one. Peace out.